Good morning, dear students. Welcome to another session of Verilog HDL. So, in previous sessions, we were discussing regarding data flow modeling. So, in that we discussed regarding assignment statements. Then we discussed regarding the delays, and we started off with expressions, operands, and the operators. So, in operators, we discussed a few of the operator types. That is what is meant by arithmetic operators, how they can be utilized, what is meant by unary, binary, and ternary operators. Then we discussed regarding logical operators, how logical operators are different from bitwise operators. So that also we discussed. Then relational operators, equality operators. So these are bitwise operators, how these operators are different from that of the logical operators. So these aspects also we discussed, and we looked into the examples. Next, we came around with the reduction operator. So wherein bit by bit operation is performed, and it requires only one operand. Therefore, it is a unary operator. It requires only one operator. Therefore, it is unary operator. We discussed even regarding the shift operators. What happens when right shift is performed? What happens when shift is performed? What happens and in the vacant place? What data is put in? So those all discussions we had done in previous class. The major thing what we had discussed in previous this thing was concatenation operator, and the other one was the replication operator. Okay, so concatenation operator is given in this form, that is open braces with the comma, open brace, comma, and a closed brace. Repetition operator is that is open and closed brace together. So it is specified in these forms. So we discussed regarding what all things can be concatenated, how the concatenation can go ahead. We can perform, say, a bit by bit concatenation or just part of it. So all these things we had discussed. So coming down to the next operator, that is conditional operator. So even in C programming, you have observed that there is a conditional operator which is having the same representation. That is a question mark and a colon together give you the conditional operator. Now, how the conditional operator is utilized? So in this case, you specify a condition. You specify a condition. So if this condition is true, then this value is utilized. If the condition is false, then the other value is utilized. So here, if we just go for an example, we'll just look out through an example. So here, what we are doing here, control is the conditional aspect what we are looking out for. Based on the value of control, based on the value of control, either in one or in two is in zero is selected. Based on the control value, well, if it is true or false, if it is zero or non-zero, based on that, we'll be selecting in one or in two. So, and that value will be assigned to this variable. So that is conditional expression is evaluated. If it is true, this value is utilized. If the conditional expression is false, this value is utilized. So this is how conditional operator works. So here in block representation, if we just check conditional expression, so you give it as input. If it is true, it will select this expression or the result of this one. If it is false, it will select the other one, that is a false expression. So that is so this is a multiplexer what he has represented here. So based on this conditional, either you select this or this. So it is like you are selecting I0 or I1. So this is a multiplexer. So this is how it is operating. That is just an example what we have specified. So here the condition expression, that is the conditional expression, is first evaluated. That is, this expression is evaluated first, and based on what is the logical aspect, whether it is true or false. If the result is true, then the true expression is evaluated and its result will be utilized. If the result is false, that is logic 0, then the false expression will be evaluated and its result will be utilized. Now, what if the result is ambiguous? What if the result is ambiguous? Because there might be chance that you are comparing two numbers and then that one number is having a x value in its bit position. One of the bits is x. That is, for example, the number is in this form. So if you're using the logical expressions, we had seen that if there is x value, then the result will be evaluated to x. So if this is the case, then what happens? So in that case, both the expressions will be evaluated and their results will be compared bit by bit in order to return each bit position and x if the bits are different and the values of the bits if they are same. So here evaluation of both the expressions are being done and their results are compared bit by bit. So each bit, that is how we compared in one of the previous cases, that is bitwise operations, right? In the similar way, bit by bit, this thing estimation is done. They are compared. So they are compared to what? They are compared to return for each bit position and x if the bits are different and the value of the bits if they are same. So here, what does this imply is, what does this imply is, now if I have some number like this and I have another number like this. So you have evaluated it and in expression, you have got this result. Say this is for true and this is for false. You can consider this one instead of this. You can do is you can consider it as 1. So now what is done? So based on the true expression and the false expressions evaluated, so this is the result what we have got. Now what is done is bit by bit comparison is done. So this bit is compared with the this bit, both are same. So that bit is returned. Then here we can see that the second bit what we are observing here is different from this one. So in this case, a x is returned at that bit position. Here again the numbers are same. So again that number is returned. Here again it is different. So x is returned. So again if there is another one number, both are same. So that number will be returned. So that is what that statement implies. So here the statement implies those things. That is, um, what if the conditional expression evaluates to ambiguous value? Then true expression and false expressions both are evaluated. And after the evaluation, the comparisons are done. Bit by bit, the comparisons are done. So once bit by bit comparison is done, what happens is based on the comparison, you'll be either returned with the value of x if the bits are different, or you will be returned with the value of same bits which are identical. So you'll be either getting x or you'll be either getting the bit which is relevant over there. If they are same, that bit is returned. If they are different, x is returned. So that is what is happening in these cases. So this is how conditional operator works around. So it is basically like a if else statement what you have, but even you have conditional operator even in C programming. So if it is like if this is true, then use this. If this is false, then use this. So it is like if else statement. If conditional expression is true, then execute the statement related to true expression. If conditional expression is false, then execute the expression related to false expression. So that is like this form. Okay. So now here we have one example what they are specifying. So we'll not bother much here. So I want to assign address to the bus. Now this assignment is dependent on drive enable signal. If drive enable signal is say is at logic 1, if it is enabled, then I have to assign the address out. But if drive enable is 0, that is enable is not activated, it is not activated, then I present the bus with a high impedance state. That is all say if I'm assuming that there are 36 this thing over there, so all these things will be assigned to high impedance state. So if drive enable is there, then only whatever is present on address out will be present in the address bus. If drive enable is say logical 0, that is false, then the address bus will be assigned with the high impedance state. So this is where you can utilize conditional operators. Then apart from this, here we can see that uh, out is the value what I have to assign. I have to assign some value to out. So I am assigning out based on the control signal. If the control signal is say logical one, that is true value. Logical one, that is true value. Then input one is assigned to out. If it is logic 0, that is if it is false, false, then in 0 is assigned to out. So this is how your ternary operator, or what we specify as conditional operator, is utilized. Now this is the ternary operator since it utilizes how many operands. So here you can see 1, 2, and 3. So three operands are being utilized, and you can see that here we have one operator and here we have another operator. Therefore, we have two operators used along with three operands. Okay, so this is the ternary operator. Conditional operator is a ternary operator which utilizes three operands and two operators. So then apart from this, just using these variables, we can use even the expressions. We can use even the expressions. So here we have one example. So what will be the value assigned to out based on this usage of the conditional operator? So here instead of control, you can see that there is a is equal to, it is checking whether a is equal to 3. So this is an expression. This is an expression. This is not an expression. This is the parameter or the variable what you are using over there. So it is register data type and other data types what we have discussed. So here you are evaluating the expression. Here you are checking the signal you can specify. You're checking the signal. But here what you're doing, here you're using the expression. Now here another one thing to note down is in this, so in simple form, if I just specify if this expression is true, then this part will be utilized or will be evaluated. If this expression is false, then this part will be evaluated. For example, in simple, if I write it as say if there is A and there is B over here. So if A is equal to 3, then this A expression will be evaluated. If A is equal to false, then B expression will be evaluated. Now another thing to observe here is you can have conditional operator looped in. It is kind of looping what you are performing over here. So conditional operator within a conditional operator. So here we can see that this is the condition. If A is equal to 3, then you evaluate this expression. If A is not equal to 3, then you evaluate this expression. So in this one, you can see that the expression itself is another conditional operator. So in which what you're doing based on the control signal, you are selecting either X or you are selecting either Y. You are evaluating and using these values. So for example, if A is equal to 3 is true, it will come to this part because this has to be evaluated. Now here, based on the control signal, let us say that control signal is also 1. So if control signal is 1, then X is selected. So the result of this expression is X. Result of this expression is X, and X will be assigned to out. Now if the other way around, if control is 0, so A is equal to 3 is true, therefore it comes to this part. This has to be evaluated now. So if control is 0, Y will be the result of this entire expression. Y will be the result of this entire expression, and this Y will be assigned to out. So similarly, if this one turns out to be false, it will come to this part and it will see whether M or N has to be obtained based on the control signal. So this is what happens in using control conditional operator. Okay. So this is regarding conditional operator. So moving ahead, operator precedence. So as in many of the programming, this thing you have seen that operators have some precedence. Like in C programming, you check out with BODMAS rule. So such kind of this thing is present even in Verilog. So here, which operators have higher precedence and which have the lowest? So here we can see that the unary operators and the multiply, divide, and modulus. So these operators have the highest precedence, whereas the conditional operator is having the lowest precedence, and the rest all fall within these. So first precedence is given to unary, multiply, divide, and modulus, and then comes the add, subtract, and shift operators. So after that, that is the second preference. The third preference is given to the relational operators and equality operators. And the fourth, this thing is provided for reduction operators and logical operators. And the last one is for the conditional operators. So why these precedences have to be known is, suppose if we give an expression which contains all these operators, so you should know how the operation will be performed, how the operation will be performed. That is, so if I give you an expression like a right shift two times, if I put bracket, then if I add 2 to this, then as say divide this by 3, so something I put it in this form, you should know how this expression gets evaluated. So based on the precedence, we have to identify what will be the result. Now, if you don't follow the precedence rule, what happens is what expression you have evaluated might not be matching with what you are getting in the simulation or the execution part. So you should know what precedence the operators are having. Okay. So let us look at one example, and the other examples are in similar form. So in previous this thing, right, in gate level modeling, we had discussed regarding 4 to 1 multiplexer. We had discussed even 4-bit full adder. So we can implement all those using, say, your data flow, sorry, your data flow modeling. We can go ahead with the data flow modeling. So in your gate level modeling, right? mm, So here we can observe. So in gate level modeling, we had 4:1 multiplexer. So now how did we solve it in gate level implementation or gate level modeling? We first looked out at its overall structure. So it will be containing two, since it is 4 is to 1 multiplexer, right? It will be containing two select lines and four input lines. So based on what is the value of S1 and S0, one of these lines will be selected and presented at the output. So this is what multiplexer does. So here is the truth table related to that. If S1 and S0 is 0, 0, I0 is selected. S1 and S0 are 0, 1, I1 is selected, and similarly up to I3. So this is how it goes around. So I got to know what is the truth table which we have to utilize. Now here you can see that S1 is 0 and S0 is 0. So when it is 0, 0, then only I0 has to be selected. Last one, if you just check, if both are 1, then only I3 has to be selected. So now these things have to be expressed in terms of, they have to be expressed in terms of logic diagram. They have to be expressed in terms of logic diagram. So here you can see that logic diagram of the 4 is to 1 multiplexer. So for this one, this is your top level model, how it will be appearing. This is your top level model. And within this, you will be having the modules instantiated. Say the AND module is instantiated, XOR module is instantiated, not gate is instantiated. So here you get the gate level details of what all gates are present and how they are interconnected. Now, for example, if I just look over here, what you can just see S1, S0. Say I want to choose I0. Say both are 0, 0. So let me assume that both are 0, 0. How it will be selected? If both are 0, 0, this goes to the inverter. Here it will be 1. So this line goes to this. Now next, this is also 1. So here if I just follow, this goes here. So here I0 is there. So both are 1. Both are 1. That is S1 is 0, S0 is 1. But when it goes to the inverter, both gets converted to 1. So the input to this gate is 1, 1. And another input is I0. So for example, if I consider if I0 is 0, what happens? 0 ANDed with anything will be giving me a 0 value. If I0 is 1, what happens? It is 1, 1, 1. So the output also will be 1. So here, no matter what it is, whatever value of I0 is there will be presented at this point, that is here. At this point, it will be available. So this value will be coming over here and will be presented with the output. So again, logically, I have to analyze all these, and this circuit logic diagram will give me the implementation of the multiplexer. So this is logic diagram representation. So first the general view, then we came across the truth table. From truth table, if you want, you can obtain the expression and try to see how the logic diagram will be looking up. So this is how it will be looking. So now that is what they have specified. So in gate level modeling, what we had done, we can see that the port list is specified, it is declared over here, and then you are specifying wire. That is how the interconnections, that is these interconnections which are present. So it is like you're taking the breadboard and making the connections. So now in this case, so what is the input to the NOT gate? Input to the NOT gate is S1 and S1N is the output. Here S0N is the output and S0 is the input. So you have to specify those all things. So not, then you have the four AND gates which are there, and lastly the OR gates which is present over here. So out is the output and these are the inputs. So you had specified, you had obtained the 4 is to 1 multiplexer in this form in your um, gate level implementation or modeling. Now the same thing, if I come to say the data flow modeling, how it goes around, how I can implement it. So we can see over here, the first method what is specified is using the logic equations, using the logic equations. So let us look at the code directly. So here we can see that there is a module which is a keyword. This is the name of the module. This is the parameter list. So that is I not I1 this along with this and this parameter. So this is the ports. These are the ports. So this is the port list, and you define provide the port declaration. Which one is input? Which one is output? Whether all are input, all are output. Whether input output is also present. So you specify the port declaration. Now what I want to do is I want to use these ports to see what should be assigned to out. So here based on the select lines, out will be presented. That is if we have 0, 0, I0 is selected, 0, 1, I1 is selected, and so on up to I3. So this is how the logical expression can be implemented. So when you put it in K-map, it will be ending up in the logical expression. Even in for if you're implementing adder, right? For addition, you require XOR gate. So in that XOR gate, you have the expression. So you can write that expression directly. So here what we are doing is we are using the logic equation. So here it is like if I equate this one, if I equate that, so S1, S0, and output is there. So it is 0, 0, 0, 1, 1, 0, and 1, 1. So here it will be I0, here it will be I1, here it will be I2, here it will be I3. So your output Y is actually like S1 bar, S0 bar into I0 plus S1 bar, S0 into I1 plus S1, S0 bar into I2 plus S1, S0 into I3. So this is a logical expression for the 4 is to 1 multiplexer. This is a logical expression for 4 is to 4 is to 1 multiplexer. So now here we can see here what is the value assigned to out. So value assigned to out is again dependent on this expression. Dependent on this expression what we have specified. So here you can see. So S1 and S0 is there. What should be the value of these? It should be S1 bar and S0 bar. So that is negation of S1, and this is ANDing. This is ANDing. So it is S1 bar ANDed with S2 bar ANDed with I0. So it is ANDing with this one and ANDing with I0. Since all are one bit in this thing, so no need to specify any other stuff. So it is ANDing of these bits. ANDing of these bits. So it is S1 bar ANDed with the S2, S0 bar ANDed with the I0. So this is how it goes around. So similarly, next one, if you just see what you are having, it is S1 bar ANDed with S0 ANDed with I1. So it is negation of S1 ANDed with S0. There is no negation over here. ANDed with S0 and I1. So similarly, in the last one, you can just check it is S1 and S0 and I3. So this is how you implement it using logical expression or equation. So you obtain the equation, and this equation itself, you try to put it in your Verilog code using the assign statement. Using the assign statement. So if you just check it with this one, so here what you had to do, you had to specify the internal structure. That is these internal signals, intermediate signals which you are getting. So you have to specify those, and what is the input to this and what is the output. So that you have to specify. So it is basically like you are specifying which wire is going to which pin. So this is something in this one and how they are interconnected. So here again you have to specify separately. You are instantiating the AND module wherein you are trying to see what is the output and what is the relevant input to that. So that is what you are trying to see. So here for example, if it is just 4 is to 1, if it is say 16 is to some other this thing, 16 is to 1, then what would happen? If it is say more than 16, 32 is to 1. So imagine you'll be having how many how many select lines. So based on those select lines, you are having 5 select lines. You should remember each and every stuff over there. So it becomes difficult when the complexity of the circuit increases. Even by a small amount, if it increases, it becomes complex enough. So you should remember what input is to be given to this gate, what input is to be given to this gate, what are the inputs that have to be given to this gate. So all has to be remembered in gate level modeling. But in this case, if you know, say, the logical expression, if you know the logical expression, say in adder you have so this is the adder, that is full bit, one bit full adder. So here you know the expression, but here you can see that you have to specify how these connections are being established and what is the result it will be giving. So instead of that, if I am able to assign directly with the help of this XORing operation, then it is more than sufficient. So this actually increases the complexity. When the circuitry increases in complexity, and then implementation and gate level modeling also becomes tedious. So therefore we can move to data flow modeling. So this is what is happening in this case. So this is much easier compared to gate level modeling, because abstraction is again presented in a much higher form. So you're not bothering about how the negation is done. You're not bothering about how the ending is done. So it is indirectly what you're doing is negation. So this will be performing this operation. This will be performing operation similar to this. So it will be doing not of this one, and it will be giving you this signal. So you're not bothering about the intermediate connections which are there. So indirectly you are utilizing those stuffs. So no need to remember not and these things. So if you know the operators, right, that is how you can go ahead. Now there is another way of actually implementing 4 is to 1 multiplexer, that is using conditional operators. So here what happens is, so you can see that you have two this thing, S naught, S1 and S naught. So based on these two values, you either select this one or you either select one of these input. So based on this table itself, you can identify what can be the conditional expression evaluated to. So here we can just check out in this case, what he has done is he has used, he has looped in the select lines. He has looped in the select lines and he has utilized the conditional operator. Here you can see that out is assigned with one of the values of I naught, I1, I2, I3. So how he is doing that? He is doing based on the values of S1 and S0. So what is the first thing he does? If S1 is true, that is if S1 is 1, what is the other possibility of S0? S0 can be either true or false. It is like S1 is 1, S0 can be either 0 or 1. So if it is 1, I3 has to be selected. If it is 1, I3 has to be selected. So if S1 is 1, this part has to be selected. So then what should be S0? S0, if it is 1, then it is like S1 is 1 and S0 is 1. You have to select I3. If S1 is 1 and S0 is 0, then you have to select I2. So here he is doing the same thing with the help of conditional operator. So here you can see that if S1 is 1, this part will be evaluated. If S1 is 0, this part will be evaluated. Now let us just check for 0. So if S1 is 0, S0 can be either 0 or it can be either 1. So if it is 0, it implies that it is 0, 0. Then which one has to be selected? I have to select I naught. So what does this imply? If S1 is false, then I have to come this, evaluate this expression. If S0 is also false, then I go to the false expression. That is I naught. I naught will be assigned to out. So similarly for other conditions. So this is how the implementation for 4 is to 1 multiplexer is done using conditional operator. So there are other few examples. You can just check out how you can go ahead with the implementation of these things. So just one example, if I just check. So here you can see what is the direct, this thing, only one statement he has provided, C underscore out. That is, this is concatenation what you're doing. Because what happens is if you're adding numbers, so this is 0, carry over 1, this is 0, this is 1, and carry over 1. So this is C out, and this is the sum result. So that's why you're concatenating. So overall, this represents your result. So C out, comma, sum will give you the overall result. So here what you're doing, you are using the plus sign directly. You're using this plus sign directly. You're not bothering about any other stuff. So here there is an example of carry look ahead adder. So you can just see how it can be implemented. Okay.